We were discussing about context-free languages. We learnt about two formal representations for context-free languages. They are context-free grammars and push-down automata. And we proved that they are equivalent. And also we have seen that deterministic push-down automata are strictly less powerful when compared to non-deterministic push-down automata. We also have looked at the pumping lemma, and we used a game induced by a language to prove that certain languages are non-context free. Using that, in the previous lecture we proved that the language a raised to n, b raised to n, c raised to n for all natural numbers n is not a context free language. Today we are going to finish our discussion on context free languages, and the topic for today is closure properties of context free languages. I hope you remember about closure properties from the lecture that we discussed closure properties of regular languages. Anyway, we can recollect the basic aspects about closure properties. A context free language is basically a set of strings. So it is a set. Closure properties of any set S is the operations which take element or elements of S and produce an element of the same set as output. Thus, closure properties of context free languages are those set operations which take context free languages or a context free language as input and produces a context free language as output. For example, we shall see whether the set union operation is closed under context free languages. Whether the context free languages are closed under the set union operation, that is, can we prove that the union of any two context free language is also a context free language? If we can prove, then we can say that union is a closure property. We can try to see that is set union a closure property of context free languages. If the answer is yes, that means if you take the union of any two context free languages, then the result must be a context free language. So what is the answer? What do you think? Think about the formal representation of context free languages, and can you say what it is? Is the set union a closure property? The answer is yes. So we have to state it as a claim and prove it. If it is closed under set union, then this is the claim. If L1 and L2 are context free languages, doesn't matter what is L1 and what is L2, they are context free languages is what we know. Then their union must be a context free language. If we can prove this claim, then this answer is correct. We can try to prove it. Suppose L1 is a context free language then we know that there exists a context free grammar G1 such that the language L1 is generated by the grammar G1. Similarly, if L2 is context free, then there exists another grammar G2 generating the language L2. Now, without loss of generality, assume that there is no common variable in G1 and G2. Variables are also called non-terminals. Assume that their intersection is empty, meaning no common variables in G1 and G2. How can we assume it without loss of generality? Because if you have some common variables, you rename them so that in the resulting grammars there is no common variable. That you can easily do, and that is why I say without loss of generality, assume that the intersection of the variable set is empty, no common variables. Now, we can define a grammar G3 with a set of variables, set of terminal symbols, a start symbol and a set of production, where the variable set is all the variables in the first grammar union all the variables in the second grammar. In addition to that, we are adding one more variable S3, which is going to be the start symbol of that grammar. Okay, and productions, the terminal set is same, and not that L1 and L2 are over the same terminal set or alphabet set, and that is the same for this grammar as well. And what is S3? The start symbol is the newly added variable, and the only thing to define is the set of productions. And what is it? The set of all productions in the first grammar union the set of all productions in the second grammar plus one more production. What is it? The start symbol goes to either the start symbol of the first grammar or the start symbol of the second grammar. That is the only added production. Now you can easily argue that the language of the grammar G3 is precisely the union of the the union of the languages of the grammars G1 and G2, that is L1 union L2. It's very easy to argue. Suppose that W is a string generated by the grammar G3, not that S3 is the start symbol. Then in the first step, either you have to apply this production for S3 or this one. Assume that you are applying S1. That is the first step, you are selecting S1. What is S1? S1 is the start symbol of the first grammar, and then you derived something means it is in the first language. And similarly, if it is in the first language, then you can derive it from S1, and using the first production you can derive it from the simple S3 as well. And similarly, you can prove when it is present in the grammar L2. The only difference is that in the first step you will be applying this production. The proof is very easy, and hence we prove that the constructed grammar is generating the union of the languages L1 and L2, and thus conclude that if L1 and L2 are two context-free languages, then their union must be a context-free language, and hence set union is a closure property of context-free languages. Okay. Proceed and look at the next operation, which is Kleene iteration. What is Kleene iteration? You can prove that it is closed under Kleene iteration, and recall that if L is a language, the Kleene iteration of L is L raised to 0 union L raised to 1 union L raised to 2 union, etc. This is an infinite union, And what is L raised to 0? By definition, it is the language containing only the empty string. L1 is the language itself, L square is the concatenation of L with L, and LQ will be the concatenation of L square with L, and likewise it goes. I hope you remember this definition from the basic lecture that we have in this course, where we discussed about the basis of formal languages. We claimed that it is yes, so this is actually the claim. If L is a context free language, then L star must be a context free language. We need to have a proof, and suppose you have L as a context free language, then there exists a context free grammar G generating this language. Now from G you can define a grammar G prime with the same set of variables, same set of terminals, same start simple, but production set is different. In what way it is different? You are adding two rules into it. What is it? The start simple can be replaced with SS or epsilon is the only production that you need, and you can claim that the new grammar G prime can generate L to the power I for all values of I greater than or equal to 0. How will you argue? You know that by applying this production for S, replacing capital S with epsilon, you can derive the string epsilon, and hence L raised to 0 is there, because epsilon is the only string in L raised to 0. And you have the set of all original productions here, so definitely you can generate the language L to the power 1. Now if you apply this production, what is this SS, then from S you can derive the first language, that is what we are given with, and from the second S also you can derive any string in the first language, in the given language. That means by using this you can generate any string in L square. And if you apply this production again here for S, you will get this sentential form, and which can derive any string in L raised to 3. Similarly it goes, and hence you can derive any string in the language L to the power I. So now we have constructed a grammar G prime which is generating the languages L to the power I for all I. Okay, now it remains to prove that the union is also a context free, which we already have proved, and hence we can conclude that L star is context free, because we already proved that context free languages are closed under set union. Here we proved that all these languages are context free, and now L star is their union, and we already know that context free languages are closed under union, and thus we proved that context free languages are closed under Kleene iteration. Now proceed. Now we are asking this question: is intersection a closure property of context free languages? We proved that it is closed under union and also closed under Kleene iteration. So what is your guess? Are context free languages closed under intersection? The answer is no, they are not. So we need to state that claim. The claim is that they are not closed under intersection, and we are going to prove it using the method of contradiction. So for the method of contradiction, we just need to get a counter example for two languages L1 and L2 such that their intersection is not a context free language. If we can get two context free languages L1 and L2 such that their intersection is non-context free, then this result is correct. So I am giving you two such context free languages. Consider the following context free grammar. This is the first context free grammar with the productions. You can see here. You can see that this is a context free grammar because all the productions in the RHS contains strings over variables and terminals. Now you can prove that the language of this grammar is a to the power n, b to the power n, c to the power m, where n is greater than or equal to 0 and m is greater than or equal to 0. The number of a's and b's are same. And how will you prove it? Note that here from the start simple, the first variable that you are deriving is capital A, and from capital A it is very easy to see that you are deriving a raised to n, b raised to n. Okay, and what is the second simple? It is capital B. From capital B you can derive 0 or more c's, and so it is easy to see that. And now look at the productions of the second grammar, which is again a context free grammar, and you can prove that the language is this: a to the power m, b to the power n, c to the power n. Number of b's and c's are same. And see here, the first simple is capital X, from which you can generate 0 or more a's, so that is done. And the second simple is y, from which you can derive equal number of b's and c's. So these are the languages, but if you take the intersection, what you are getting? Suppose context free languages are closed under intersection, definitely their intersection must be a context free language. What is their intersection? If you take the intersection of these two languages, a string to be in the first language, the number of a's and number of b's must be same, and for a string to be in the second language, the number of b's and number of c's must be same, and hence for a string to be in both L1 and L2, the number of a's, b's and c's must be same. Okay, this is the intersection, and which is proved to be a non-context free language. In the previous lecture we proved that this language is non-context free, and thus we are getting a counter example, and therefore we can conclude that context free languages are not closed under intersection. Now moving to the next set operation, which is complementation. Question is complementation a closure property of context free languages? Or in other words, can we say that the intersection of, the complementation of any context free language results in context free language only? Is that true? The complement of any context free language is context free. So what do you think? The answer is no. We can easily prove it by applying the De Morgan's law. Suppose context free languages are closed under complementation, then we can prove that context free languages are closed under intersection, which is a contradiction because in the previous slide we proved that they are not closed under intersection. Now let L1 and L2 be two context free languages. Now you can define their intersection using De Morgan's law as L1 complement union L2 complement the whole complement. The complement of L1 complement union L2 complement. So, this is a well known result from set theory, De Morgan's law. Now, suppose context-free languages are closed under complementation, then because L1 is a context-free language, L1 complement must be a context-free language if the context-free languages are closed under complementation. Similarly, because L2 is context-free, L2 complement must be a context-free language. And we know that context-free languages are closed under union, that we proved today. So, union of these two context-free languages must be a context-free language. Now, you apply your assumption that complement of a context-free language is context-free, then you are getting that the RHS is a context-free language which is nothing but the intersection of L1 and L2. So, you are proving that the intersection of two context-free languages is context-free by assuming that context-free languages are closed under complementation, which is a contradiction, and hence we proved that context-free languages are not closed under complementation, because we already know that this language is not context-free always. Okay, with this we are finishing this lecture. Today we discussed about closure properties of context-free languages. We proved that context-free languages are closed under set union and Kleene iteration, and we proved that they are not closed under intersection and complementation. If you recall, regular languages are closed under all these operations and most of the set operations, but context-free languages are not so, they are more complex. So, with this we are finishing our discussions on context-free languages. In the next lecture we shall discuss about the next powerful class of languages in Chomsky hierarchy, which is about context sensitive languages. We shall start discussing about a grammar representation for context sensitive languages in the next class. Thank you.